Thanks very much. Just to remind you where we got to last time, we were studying this initial boundary value problem for the heat equation on the finite interval 0, 1 with inhomogeneous boundary conditions. I'll just make that change very quickly. I think I called them GJ. So we implemented stage 1 of the method, right? So at the end of that, what have we achieved? Well, we firstly, at the beginning of stage 1, we assumed that there exists a solution on the whole closed space-time rectangle for this problem, or rather, actually, we only assumed that it satisfied these two equations. We didn't use the boundary conditions at all yet. Under that assumption, we obtained this Ehrenpreis form, which has this very nice x and t dependence just in this exponential, and it's valid for all taf greater than or equal to the time at which we're interested in evaluating. And then, I guess actually first, we derived this global relation, which was originally written in terms of t, but obviously t could have been any number, so I just changed it to taf because that's going to be more convenient later on. So what are all these objects? So this is the finite interval Fourier transform of the initial datum, so that's a thing we know. This is the finite interval transform of the solution at time taf, so that's a thing we don't know. That's kind of what we want to find, right? And then these FJs, these spectral functions, are certain time transforms of the boundary values, the Dirichlet and Neumann boundary values of the solution. Okay, so the global relation is just an equation that relates all of those. We'll talk more about why that might be useful in a bit. But from the global relation, we got this formula, the Ehrenpreis form, which gives a formula for the thing we want to find, the solution, in terms of Fourier transform of the initial datum, so that's fine. But then also these contour integrals. So D plus was the upper quadrant of the complex plane, and D minus was the lower quadrant of the complex plane. So contour integrals around those of these four transform boundary values. Okay, so we observed very quickly that at the end of the last lecture that we know this one and this one, because these are just transforms of our Dirichlet boundary data that we have specified explicitly. But we don't know these two, so we need to perform a data to unknown map. To formalize this, I guess we're going to say, let's also assume that Q satisfies, as before, the PDE and the initial condition, and also the boundary condition. Well, then we see that F0 of lambda 0 taf, that's this one. That is just integral from 0 to taf, e to the lambda squared s, g naught of s using the first boundary condition, ds, which I'm going to get a shorthand for h0 of lambda taf, and similarly f0 of lambda 1 taf, so that's the Dirichlet boundary value at the right. That's got a very similar formula, but it's in terms of the other boundary datum, and I'm going to call that h1 of lambda taf. So this is just to emphasize that these h's are things we know. These are data of our problem. They are both known. Okay, so it would be fun to try and just make some more measurements, and write down what these are, right? But we can't do that because then we've got an overspecified problem. There's going to be some kind of inconsistency between our Dirichlet and Neumann boundary conditions in general, so we definitely can't specify these as part of the problem. That would be an overspecified problem. Instead, we're going to need some kind of equations in order to work out what those two things are. Well, we have an equation involving those two things. Here it is, the global relation. So here's one of them, and here's the other, right? So this is an equation involving those two things. This is something we know, this is something we know, and this is something we know. So that's a good sign. The problem is we don't know this. So, well, let's write it down anyway. So after applying the boundary conditions, the global relation becomes f1 of lambda 0 taf, so that's the Neumann spectral function at the left, minus e to the minus I lambda times the Neumann spectral function at the right. This is minus I lambda h naught of lambda, h naught of lambda taf, plus I lambda e to the minus I lambda h1 of lambda taf, plus q naught hat of lambda minus e to the lambda squared taf q hat of lambda taf. Okay, so what have we got here? This is the unknown and things we want. All of this is known explicitly in terms of the data. And then there's this bit. We definitely don't know what it is, but what we really want to do is substitute in for these values. So I guess we don't care what it is exactly. What have we achieved here? Well, apparently nothing. We've introduced a new equation in our two unknowns, but introduced a new unknown as well. New equation, only one, right? We've got two unknowns, we should have two equations if we want to hope to solve it. But also a new unknown, q hat of lambda taf, the Fourier transform of the solution of the problem at time taf. Does this help? Well, I hope to convince you over the next few minutes that actually it does. Okay, so I beg your indulgence to just pretend this isn't a problem for the moment, right? Let's pretend that somehow magically later on we're going to deal with this bit. Okay, let's ignore that and just think about the fact we've only got one equation. So in other words, I'm pretending this is part of the data of the problem for the moment. Well, do we really have only one equation? No. We have two equations. Study this formula. If you put minus lambda into this formula, you don't make any change, right? So fj of minus lambda x taf is fj of lambda taf, right? Because this formula depends on lambda only through lambda squared. This symmetry allows us to get two equations out of this, right? So if you put minus lambda in, then this is going to change. So we now have a different linear combination of these two objects that we care about. So that's a different equation, and it's a linearly independent equation. And then we're going to get some changes here. Actually, these h's are not going to change either because of the way h was defined using the same transform effectively. But this is going to change, and this is going to change a bit. Okay? The identity map and lambda to minus lambda give two linearly independent equations from the global relation. All right, so now we've got a system of two equations. They're linearly independent. We're pretending that we know what this is, so we can solve it. Okay. I write it down as a system. So that's the Neumann spectral function at the left and the Neumann spectral function at the right, the two things that we want to find. This is m of lambda, m of minus lambda, plus vector of the two Fourier transforms, minus e to the lambda squared taf vector of Fourier transforms of the solution. Where I've run out of colors. I haven't run out of colors. This bit is m of lambda, including the minus at the front. Okay? So that's just a notational convenience so that I don't have to write that stuff lots of times. But it is also sort of nice because it means that I split the right-hand side into part that depends on the boundary data, part that depends on the initial datum, and then the other bit. Okay? So these are data, and this we're pretending it's data for now. Okay. Now, each of these vectors has the same property, right? It's some function of lambda in the first entry and some function of minus lambda in the second entry. I mean, of course it is, because that's how we got the second equation, right? But I'm now making this observation in order to make a sort of notational simplification. If we want to solve this equation, then we can use Cramer's rule, right? So we need a ratio of determinants. So let's write down those determinants. So delta of lambda is minus twice I sine lambda. And zeta plus of lambda phi for an arbitrary function phi is minus phi of lambda e to the I lambda plus phi of minus lambda e to the minus I lambda. So then if phi, for example, is m plus q naught hat plus e to the minus lambda squared taf q hat, that's going to give us the determinant we want for the first entry. And similarly, zeta minus, that's just minus phi of lambda plus phi of minus lambda. Okay. Well, then, if you look at the things we want, we get that I lambda times the Neumann spectral function on the left, plus, sorry, times the Dirichlet spectral function on the left, plus F1, sorry, so this is the Neumann spectral function on the left. I care about that because that is exactly the thing I want to substitute in here. That is now I lambda h naught of lambda plus zeta plus of lambda with the function m plus the function q naught hat over delta of lambda plus e to the lambda squared taf zeta plus of lambda q hat over delta of lambda. And there's a very similar formula for the other sum of spectral functions, which I'll just write down here in case we need it later. So now we want the spectral transform of the Dirichlet data at the right. And now then this is going to be exactly the same, except I'm using zeta minus. Instead of zeta plus. Okay. So once again, everything up to here is data on the right-hand side, and all the remainder is things that we've been pretending are data but really aren't. So if we substitute in those formulae into the Ehrenpreis form, then we're going to get some stuff that's involving integrals of data and then some stuff that's not. So yeah, I will write out this formula actually, because it's going to be good to refer back to it. So e to the I lambda x minus lambda squared t times the Fourier transform of the initial datum. So the first integral has not changed at all, minus integral around the boundary d plus of some data, i.e. this bit, minus integral around boundary d minus of some other data. I'll call that data prime. And then, oh, hold on. These pluses should be minuses. Sorry about that. Yeah. Plus integral around boundary d plus e to the I lambda x e to the lambda squared taf minus t zeta plus of lambda times lambda and the Fourier transform of the solution at time taf over delta. And then the other term I'll just write out a little bit more explicitly. Oops, integral around boundary d minus e to the I lambda x minus 1 e to the lambda squared taf minus t. And then I'll just write out what that numerator is, or what the equivalent of that numerator is for the other one. So it's minus q hat of lambda taf plus q hat of minus lambda taf, all over e to the minus I lambda minus e to the I lambda d lambda. Yes. Okay. So it's worth noting that I didn't just substitute in, right? I did a little bit more than that because I split up the integral over boundary d plus into 2. Similarly, integral over boundary d minus. And that's something we should justify, right? So the original integrands, when they were written way back on the left-hand side, they were of nice, smooth functions that you can definitely integrate. But now we've got ratios, and the denominator has some zeros. So it's possible that although this bit and this bit add up to something nice and well-behaved and integrable, maybe when you split it up, that doesn't work, right? Well, if you think about where, just sketch this quickly. So this is our d plus, and this is our d minus. Well, zeros of sign are on the real axis, so it's all okay, except at 0. Right? There's only one pole that we've got to be scared of here. And it turns out, with a little bit of work, you can see that actually that's a removable singularity, so it's not going to be a problem. Now, that's not generic, right? So it happens that it's a removable singularity here, so I'm not going to go into the careful complex, the sort of contour deformation you have to do. But in principle, what you want to do is you want to go, you realize that like where your zeros of your denominator are, you go way back over here and say, okay, well, this is a nice analytic function, so I can make a finite contour deformation away from each of those zeros. That's my new version of the Ehrenpreis form. It's still perfectly valid. And then make the substitution. Right? We could certainly do that to deform away from 0 if we like, right? We can just take those contours. That's fine. And if you look at other equations, if you look at linear Schrodinger equation, then you'll find that d plus is, or, well, the whole picture is rotated by pi by 4. So you're now looking at d plus is the first quadrant, right? So, and you're still going to have exactly the same delta. So now you've got to avoid infinitely many poles, right? So you're going to have to make lots of these contour deformations, but you do it, and that's fine. Okay? All right. So that's the first thing we have to be worried about. Secondly, these are infinite contour integrals, right? And we decomposed this thing additively into 2 bits. The original contours, the original contour integrals, even though the contours were infinite, they converged, but there's no reason that each of these should converge necessarily, right? Got to be careful of that as well. Okay, that bit I will address properly. So what I'm going to do is I'm going to actually go one better than that. I'm going to show that not only does this integral converge, but it converges to 0. Right? So if I show that this converges to 0, then definitely this still converges. But I've done even more, because that means that the only part of this representation that involved something that's not data is 0. So this is gone. And exactly the same over here happens. So that means that then we've really got a solution representation, right? So we aim to show the integrals involving Fourier transform of the solution at time taf evaluate to 0. Now, I'm not claiming that the integrand is 0, I'm claiming that the integral is 0, right? Okay. And we're going to use our favorite tool, Jordan's lemma. So these integrals, I'll leave that up for the moment. So these integrals are, well, I'll work on this one because the formula is very slightly simpler. And then I hope you can believe me that the other one works as well. So this is an integral around boundary d minus, so that's this integral. So what I'm going to do is I'm going to use Jordan's lemma to close these contours together and show that we end up with 0. So the ratio, by which I mean that bit, the whole ratio there, in this integral, well, you can see it there, and it has components that look like e to the minus I lambda, q hat of lambda t, e to the I lambda, q hat of minus lambda taf, and e to the lambda squared taf minus t. Now, these two, as lambda goes to infinity anywhere within d minus, that means the imaginary part is becoming a large negative number, so these two are going to decay. But these two do the opposite, they blow up. And this one, because of, so taf, remember way back at the beginning, taf is at least as big as t, so this is positive. So if we take anything in here, then e to the lambda squared taf minus t is going to be in the left half plane. So this decays, or at worst, it's oscillatory. And these are all as lambda goes to infinity within the closure of d minus. Okay. Integrate by parts in those Fourier transforms, integrate by parts in S, in those Fourier transforms, and that tells you that that ratio is, order of lambda to the minus 1, uniformly in the argument of lambda as lambda goes to infinity within closure of d minus. Okay, so then what do we have to say? Well, this is the Fourier transform of a nice smooth function. This is the Fourier transform of a nice smooth function. These are analytic. The whole integrand is analytic. So by our corollary to Jordan's lemma, integral around boundary d minus of e to the I lambda x minus 1 times that ratio is 0. And you get something very similar for your integral around boundary d plus. Okay. So this integral is 0. And this integral is 0. And now we've achieved it, right? because this is known, this is known, this is known. We really have a solution representation, right? A solution representation that we can actually evaluate. We can put in what our Q0 is into our computer and what the well, these data are in terms of the boundary value at the boundary datum at the left, and this is constructed out of the boundary data at the left and the right. We can evaluate these integrals. I guess they're double integrals. We can compute this. Okay. So we've finished stage 2 now. What have we learned? Well, we've learned that every solution that exists must satisfy this equation, which I'm going to call the solution representation in terms of TAF. Okay, so TAF is buried in here, right? Because there's TAFs. But this equation is explicit in terms of the data, and therefore we've got unicity for free, right? There's only one. Just from assuming there exists one, we've got a formula and that there is only one solution to this problem. Okay. Now, this formula works for every TAF that is between t and final time inclusive. So that means that we can use whichever formula is more convenient, right? So if we were doing asymptotics, I guess we'd probably want to use TAF as t. But if we were just trying to evaluate quickly, then we get a very nice x and t dependence entirely contained within here. So that's going to be advantageous. In this, where are we? Here. Yeah, so it turns out that actually, if you go through the integration by parts argument, you'll see very quickly that this result holds not just in the closure of D-, but actually in the closure of the lower half plane. Right? That's something that you can check very quickly. So it kind of appears that maybe we didn't need to go through this whole effort of deforming down to this contour, at least when TAF equals t, right? So sorry, that contour deformation only works when TAF equals t in the whole lower half plane. Okay, that's a mirage. That works for this equation and very, very special higher order equations with very, very special boundary conditions only. Okay, so although this is true here, don't think of that as in any way generic. You really do have to make these contour deformations way back that we did at the end of stage 1 in order to make this argument work in any kind of generality. Okay, that's the end of stage 2. So now for stage 3, remember what we were going to do is say, okay, throw away everything we assumed. And now just take this solution formula, or it's not really a solution formula now, it's just a formula that defines a function. Take this formula and see what happens. See what happens if you plug it into this initial boundary value problem, check whether it works, right? Yes? Sure. So I haven't explicitly constructed a map, right? What I've done is I've taken in the data which appear in here, and they're buried in M as well, right? And here are the unknowns, right? And so the data to unknown map appears to depend on these bits. So I haven't really constructed it. That's absolutely true. But what I have done is I've done something good enough, which is to say that this works because these things disappear when you take the integrals that you're interested in. Okay? So yeah, maybe it would be better to call it a good enough approximation to a data to unknown map. I'm still going to abbreviate that to D2N if that's okay.
To that, you could, though.
Oh, absolutely. Yeah, you could go further. Yeah, you could invert. You could individually invert these transforms, well, Tom showed us a great way to derive a transform inverse transform pair earlier. Yesterday, sorry. That would be a way to derive that inverse transform if you like. Or you could just pull it out of the Fourier transform with a bit of change of variables. Yeah, so you absolutely could do it. I guess what I'm... Absolutely, yeah. It disappears, yeah. I'm not going to do that because the point is I don't care, right? I don't actually want to produce a data to unknown map. What I want to do is solve the problem. And yeah, this is good enough for that. Okay. So, hold on. I lost something. Okay. So let's have a go at stage 3. So now define Q of xt using solution representation. I'm going to take it at taf equals final time. And we're going to check if it solves the problem. Okay, I'm going to start off by justifying some uniform convergence. Uniform convergence of the integrals in this equation. Well, take any xt in the domain of the PDE. It has a closed neighborhood omega within that open set. And on omega, e to the I lambda x prime minus lambda squared t prime decays to 0 exponentially, and uniformly in x prime t prime in omega, as lambda goes to infinity along the real line, or boundary d plus or minus. That's the 3 contours that we're integrating over. And because this decay is exponential, we can multiply by any polynomial in lambda, and we still get uniform convergence of these integrals. Sorry, we can multiply the integrand by any polynomial lambda. We still get uniform convergence of these integrals. So this tells us that all partial derivatives of Q exist, and they're given by differentiating the integrand. And differentiating the integrand is easy because this is the only x and t dependence. So when you differentiate the integrand, you just multiply by some polynomial in lambda, depending on what derivative you've taken. Okay? So this formula is really nice. So that immediately tells us that the PDE is satisfied. Take the partial derivatives that we know how to do, and you get 0. Differentiate in time, you multiply by minus lambda squared, minus second derivative in space, plus lambda squared, you got 0. Next is the initial condition. Well, we're going to make another Jordan's lemma argument. We're going to do that to close the contours over boundary D plus. And we're going to do that just with this integral, but just with this part of the data, I guess. No, not even that. I guess it's like m of m evaluated at capital T minus m evaluated at little t. And you observe that every t in this equation can be replaced by a TAF for any TAF from t to final time inclusive. Okay, so this is really an argument we made way back at the beginning, at the end of stage 1. But now that argument when we made it there, that assumed that Q was a solution of the problem, right? So I'm making it again now in the opposite direction and saying that it still works, right? I'm not doing it explicitly because it's the same argument. When you write down the formulae, it'll work exactly the same, okay? Okay, so what I'm really saying there is that although we originally with this equation to define Q, we could just as well use this equation it still works. Okay. So now we want to justify the initial condition. So let's set TAF to T, right? So we're going to use this equation for Q. And then set T equal to 0, all of the T's to 0. And as we're doing that, note that Hj, so that's the time transform of our boundary datum at the left and the right for j is 0 and 1. That was an integral from 0 up to 0, right? So this is 0. But then m was just a linear combination of these, so therefore m is also 0. Okay? So that means that when we evaluate this equation at t equals 0, sorry, I should have made this clear earlier. Let me do this now. So this is data, and this is data prime in this equation. Okay, so when we evaluate at t equals 0, this is gone, this is gone, this is gone, and this is gone. Okay? I'm lost. There we are. Okay, so that means that 2 pi q of x0 is the first integral. Nothing's changed. Except t is 0, so we just get this, right? And that looks good, right? Because that's the Fourier inverse transform of the Fourier transform of the initial datum. So, well, apart from the constant of 2 pi, which is appearing in where you'd hope it to be, so this looks like we might be getting something promising, yeah? Minus boundary integral e to the I lambda x. I'm just going to write it like this. Minus the other boundary integral and it turns out that these equals 0 by another Jordan's lemma. So this whole thing is now q naught of x for all x. So let's take stock. We've proved that our function that we defined using this formula satisfies the PDE and satisfies the initial condition. We've only got the boundary condition left to do. Okay? Well, 2 boundary conditions left to do. And properly, of course, we should be thinking about regularity, but as I said, I'm going to avoid such questions. Well, no, I suppose we've kind of already done it, right? Because all the partial derivatives exist. So, yeah, we did do regularity, even though I told you we wouldn't. Okay, there's something else that would be nice to do, partly because it's on the way, partly because it's just fun. If we studied the homogeneous problem, you could use Fourier series, right? So our integral representation ought to be equivalent to that representation. Yeah? Let's do that. So by Jordan's lemma, let's deform the part of these contour integrals that depend only on the initial datum, right? So split those contour integrals into 2 bits, one with the initial datum and one with the boundary data. Just look at the part depending on the initial datum. To the real line deformed away from the poles. And the poles, remember, are the zeros of delta, which, because delta was minus twice I sine lambda, are just the integer multiples of pi. What do I mean by that? Well, We started off like this. And the poles, well, I guess like that, I'll say. And the poles are here, so we're going to deform. This one, we're going to pull it down so that now goes like this. And this one we're going to pull up. So it just goes in the opposite direction. Okay, so this is our replacement for boundary D+, this is our replacement for boundary D-. And then we're also going to deform the integral along the real line up around each 0 of delta, around each pole. So now the integral along the real line goes from this to this same contour. Okay? Oops, sorry, I need to write down an identity. Which is Fourier transform of the initial datum is equal to no, actually, I can write it more efficiently. Okay, this is a true fact. I mean, you can check it in this case just by plugging in the formulae. You'll find that it's true. But it's something that's going to work in general, in fact. So that means that when you combine these two integrals that are now along the same upper contour, you've got... wait, hold on. Right, yeah, because there's a minus sign in front of one of them, right? So you've got this one minus this one, so you just get this one, right? Okay, so now we've got an integral along this lower contour times -1, and an integral along the upper contour, sorry, in this direction, times -1. The e to the minus I lambda, note, I didn't write it out. Yeah, it's kind of in here. The e to the minus I lambda is this -1. So it all matches up. And you end up with two pi q of xt is sum over k in the integers, integral around, so what I'm saying is this bit and this bit cancel out, and we've just left with a circular contour. Centered at each integer multiple of pi, radius a small enough epsilon so that they don't overlap, right? Doesn't matter what we're not taking epsilon in a limit sense, it's just small enough. e to the I lambda x minus 1 minus lambda squared t minus q naught hat of lambda plus q naught hat of minus lambda on e to the minus I lambda minus e to the I lambda d lambda minus the bits that we didn't touch, right? The bits that depend on the boundary data. Because all of this contour deformation we did only for the bits that depend on the initial datum. So e to the I lambda x minus lambda squared t times I lambda h naught of lambda plus zeta plus of lambda m minus the corresponding integral around boundary d minus. Okay, and I'll call that solution representation at time taf series. And I think I'm justified in calling it a series, even though there are integrals here, because if you solve the, if you go through this method to produce this formula with homogeneous boundary data, then that's 0, that's 0, that's 0, that's 0, so these integrals disappear. So it really is just a series. Well, okay, I guess it's a series of integrals, but this is just a residue calculation. It's a series. And similarly, if you took the Fourier series approach, then the first thing you have to do before you can actually use that is you have to shift these data somewhere else. And when you shift them somewhere else, you're going to, I guess, subtract off the long time limit, right? And when you subtract off the long time limit, that's going to do something to your initial datum. But it's also going to put an inhomogeneous term here. And that inhomogeneous term is going to show up as an integral. And if you spend some time, you'll see it's this sum of integrals. Okay. Sorry, I both overran and didn't finish stage 3, but we will get to that tomorrow. Thank you.
So you started these lectures by saying what you liked about Fourier series, what you liked about Fourier transforms. Mm-hmm. So could you comment about what you like about this method?
Sure. What I liked about Fourier series was that they were, assuming you were working in 1+1 dimensions, as I am here, fully algorithmic. And this is also fully algorithmic. So I'd love to have some folks in the discussion session this afternoon go through this method for a different equation, different boundary conditions, and you'll see that it's maybe notationally more painful, but there's no other generalization beyond that. Okay? It is a fully algorithmic method. What I didn't like about the Fourier series method was that you had to make an extra assumption, right? You had to also assume that your solution, you had to assume that your solution is expandable in the eigenfunction of your Sturm-Liouville problem, which of course is true for this problem. But it's not going to be true in general if you look at some different PDEs. Here we didn't have to assume that. We just assumed existence, and we got the solution representation, and then we assumed nothing for stage 3. We just said, let's define Q like this, and we well, almost finished, showing that it works. Okay, so that's comparing to Fourier series. Comparing to Fourier transforms, what I liked about Fourier transforms was, sorry, I'm blanking. What I didn't like about Fourier transforms is they weren't fully algorithmic. You had to somehow guess the right transform to use. Here, we haven't had to make any guesses. We've done some things that are maybe not intuitive, but you do those same not intuitive things for every problem. So once you've learned how to do it, there's no extra guessing to be done. Okay? What I liked about the Fourier transform method was that I didn't have to make any extra assumptions on the form of the solution. And I haven't had to make any extra assumptions on the form of the solution.
You got lucky there that the integrals vanished?
These ones?
Yeah.
No, that always works. Well, okay, that always works. Okay, so for, I want to formulate this correctly. It is proven, though I'm not suggesting I've presented the proof, it is proven that for a problem where this is an arbitrary monomial in the spatial derivative, and these are any homogeneous or inhomogeneous boundary conditions that look like linear combinations of the function and its first n-1 derivatives, if that's an nth order monomial, evaluated at the left and the right. And of course, you've got n of these and they're linearly independent. And the problem is, well, so under that condition, this works if and only if the problem is well posed. I'm fairly sure we can extend that a long way to having something more complicated here, such as the problems that Vishal showed us how to study, where you have dx dt terms appearing in here as well. You can also have multi-point conditions, so you're not just evaluating the left and the right, but maybe some interior points as well, and non-local conditions, so you've got some kind of integral type boundary conditions. I'm pretty sure that result is going to work, but it hasn't been gone through yet. Oh, zeta plus and zeta minus are just... I erased them, didn't I? But they were the, so I had that linear system, and I wanted to solve the linear system, so I used the easiest tool I have, which is Cramer's rule. Cramer's rule, so it's just a ratio of determinants, right? This is the determinant of the linear system, and this is the determinant of the linear system, where you've replaced the second column with these things, right? Yeah, there's nothing deep in that. It's just Cramer's rule. Yeah.
So I just wanted to pick up on the comment that you said when those integrals vanish. So I personally look at it sort of the other way, where for me a well-posed problem is precisely one where I can make that magic happen.
So that's your definition of well-posed? Well,
that's usually what guides the calculations. And in practice, right. It is my definition of well-posed. Yeah. So the boundary conditions for which this works allows you to define a solution formula that can be justified.
Sure.
And hence that is a well-posedness requirement. That's the cornerstone.
Yeah. So absolutely. So I should clarify exactly what I mean by well-posed as well. What I mean is there exists a unique solution. So I'm not talking in a Hadamard sense, though. If you look at the work of Dionysios Mantsavinos and Alex Himonas, then they show how to extend it to that setting as well. So I'm just talking about existence and uniqueness of the solution. Yeah, I think that's enough comment. Yes? Exactly, yeah. If you didn't have second order, so let's say it's third order, right? So this is just dt plus dxxx, right? So then what's going to happen? Where is it? Oh, it's here. Perfect. So this is now a lambda cubed, right? As you surmised. So then you can't use minus lambda, but you can take your primitive cube root of unity and use that. And there's two of those. So actually now we've got three maps. We've got the identity map, we've got omega lambda, and we've got omega squared lambda, if omega is your primitive root of unity. That's going to be enough because then you get three global relations together with your three boundary conditions now. So we've got a system of 6 equations in 6 boundary values. Yeah. Exactly. So it gets a little bit more complicated if this is not monomial. If you make it a polynomial, then you've got the polynomial here, and so you need to think about the maps that work for that polynomial. So you're mapping. So each of your Ds, each of your regions of D now become they're sort of curved. They're still asymptotically. They're going to this kind of sectorial shape. But you need to be careful about constructing those maps. It's proven that you can construct those biholomorphic maps. Doing it explicitly is maybe not so easy, but it's going to work through. Like philosophically, it's no more difficult.
Sorry, I might be lost, but I have a question that we are applying this transform only on X, right?
The Fourier transform is applied in X, yes.
Okay, but lambda appears to be coefficient of both t and x. I mean,
sure. So right. So you're thinking a Fourier transform ought to be like e to the I lambda dot x, where x now involves the space and time, and lambda is a vector of complex. Yeah, sure. Yeah, that's a entirely valid thing to try. It's not what I did. So what I did is I just did the Fourier transform in space, and then from that I got an ODE in time for the spatial Fourier transform of the solution. I solved that, and this thing appeared. Okay, as a result of solving that.
The rest of it is just to evaluate the solution.
Yeah, so I guess from solving the ODE and then sort of monkeying around with contours, you get this equation. That was the end of stage 1. Everything I've done in stage 2 was to get formulae for these 4. Well, I guess these 2 come straight out of your boundary conditions, but I had to get formulae for these 2 as well. So this was our data to unknown map implicitly. And then once you substitute those formulae in, you've got something that you can really claim is an effective representation of the solution.